Mm, Alright, let's have a look at problem 2317, maximum exclusive OR after operations. So for this problem, we're going to check for each bit position to see if we can set it to be 1 to maximize the result. So that's the method. First, I'll go through the statement of the problem, and then we will explain the method and look at the examples. And finally, we share the short code and do the test cases check. So first, let's look at the statement of the problem. So here we are given a zero-indexed integer array called nums. So in one operation, we can select any non-negative integer x and an index I. Then we update the numbers I to be equal to this expression, which includes AND and OR operations. So notice that the AND and OR are the AND and exclusive OR operations in the sense of bitwise operation. So we are required to return the maximum possible bitwise exclusive OR of all elements of nums after applying the operation any number of times. So the good point for this problem is that we are only required to return the maximum exclusive OR result. So we do not care about how many such operations are applied. So here are two examples. So in example 1, the return is 7. So here is an explanation. And in example 2, the return is 11. So we will look more details in for these two examples. Let's also look at the constraints. So the first constraint is about the length of nums, which can have a length up to 10 to the power 5th, meaning that we cannot solve this problem by purely brute force. Second is about the range of nums, which is less or equal than 10 to the power order 8. So this is going to be important for us. So with that said, let's look at the method and the working examples. So the method is that we check for a bit position and check if we can set it to be 1. So as long as there exists a number in nums such that this bit is 1, we can make it. So this point will be made clear after we see the examples. So here, let's consider 2 bits in order to fix the idea. So assume x and y are 2 bits, either 0 or 1. Then we look at this operation. So this operation, we will claim that if x equals y, then the result will always be 0. Otherwise, it will be x. So this is the example. For example, if x and y equals, then the exclusive OR will give us a 0. So x and 0, so is always 0. So if x and y are different, so the exclusive OR give us 1. So x and 1 always equal to x itself. So these are the examples. So what does it say? Basically, it says that so we are properly choosing y, we can make any bit of a number to be 0 or as it is. So that's the point for this operation, or the effect of this operation. So now let's look at some details for example 1 and example 2. So for this, I will write these numbers into binary representation. So 3, 2, 4, 6. The right is the binary representation. So if we look at the rightmost bit, so we have in these 4 numbers, there's 1 bit appeared. So that is an odd number. So we can set it 1 after exclusive OR. So the second to last bit, we have 3 ones. So we do not need to do any operation. So we can set it to 1. So the most significant digit or bit, if we have 2 ones, So as 1 appears, so we can do the operation to make 1 appears odd number of times, so that the exclusive OR give us a result 1. Right here we can make it 1 by setting this to be 0, for example. Or we can set this to be 0 as we like. So overall 111 is what we get, corresponding to 7. So similarly, let's look at example 2. So the right is the binary representation. So if we see this bit, it has 3 ones, so we do nothing, we set it to be 1. And this bit, we have 3 ones, odd number of ones, so we set it to 1. So the most significant bit also have an odd number of ones, we set it to be 1. But the second column, the corresponding bits are all zeros. So for this, we can only make it 0 due to the nature of this operation, right? So in other words, if it's zeros in a column, so we can only make it 0. And if in the column there are ones, so we can always make the ones appear odd number of times, so that in the exclusive OR operation, so we will get a 1. So that's the result, 1, 0, 1, 1. So corresponding to 11, that's the return. So with that said, let's look at the short code. So before we do that, we check the constraint. The constraint says that the num I is less or equal than 10 to the power 8. So if we compute log 2 of this number, it's actually between 26 and 27. Therefore, 27 bits shall be sufficient for us. So first step, I'm going to set the bit positions. I will check if I can set the bit to be 1 or not. So for this, I'll initialize a bit array, so with 27 elements, originally all zeros. And then basically we need to iterate for numbers for each of the bits. So for I in range 27, then we want to check by scan the numbers if there's 1 in the corresponding bit. So for this, I'll just iterate for num in nums. So as long as we see 1 corresponding bit at this position, we're going to break, right? So we check if this position has 1 appear. So we shift the num to the right I bit. So if this is 1, so basically we can set this bit to be 1. And then we're going to break. So if after this the loop, so we didn't set a bit, so that bit will remain 0, meaning that for all the numbers for that specific bit, so they're corresponding to zeros. So with that said, we finish the set of bit positions, and then we get the result. We just need to get the decimal representations. So for this, we will initialize the result, and then we just iterate the bits. So for I and bit in enumerate, let's see, for I in range 27. So basically we are going to add the corresponding power of 2, right? So we check if bits is 0 or 1, then we multiply the corresponding order of 2, that is I, right? Notice that in the bit, the first element corresponding to the least significant bit in the representation. So then we can return the result. So that's a full solution to this problem. Let's check for the special cases first. It passes the first one. Let's see if it can pass the second one. Oh yeah, it passes the second one. So we are in a good position to test all the cases. Submit. it passes all the case. I guess for this problem, that's about it. Basically, we are write the code by analyzing the effect of the operation, and then by examining the two examples, we found that as long as for a specific bit position there are ones appearing, so we can make that position to be 1. Right, so that's about it. Thank you very much.